Chief Commercial Officer at LioniX International, and he is going to talk about silicon nitride photonic integrated circuits for life science.
Thank you very much, and thank you very much for the invitation, for presenting our silicon nitride-based platform for sensing. What I want to do today in the next half an hour is show you some flavors of possibilities of silicon nitride-based waveguides for sensing. And I'm already going to explain the main message of the talk. It's not about chips. In the end, it's about functionality that you put in the box, that you put on the sensor. It's about building blocks and enabling that by choosing the best technology or the best platforms for that. So the sensing session about life science is of course also a container term. So it's a broad range of applications. I'm going to focus on a few of them, and I'll show that in the next half an hour. So I assume I don't have to explain what a photonic integrated circuit is. But I put this slide in to make clear the last message. Because a PIC by itself is not a product. The PIC by itself is just a piece of silicon that does something. In the end, it's about the functionalization, it's about the packaging, assembly, and how you use the module in the end. And the technology I'm talking about today is triplex. And triplex is silicon nitride, LPCVD silicon nitride based, low pressure chemical vapor deposition. We got a second speaker later this week is about Ligentech, who used the same kind of material stack, but then in a different geometry. The triplex name comes from actually 3 layers. This is the original triplex as we started it in about 2003, aiming back then for low birefringent polarization independent waveguide properties. You see here a layer of nitride, oxide, nitride, and in this direction you get the same nitride, oxide, nitride. So 3 layers, triplex, polarization independent waveguide, aiming for telecom applications. That was just after the telecom bubble burst in 2001, the holy grail of integrated photonics. We want to make money with these kind of structures for telecom applications. What we've seen in the last decade is that a big market is not about the telecom applications or about going to the data centers. A big market is also in sensing, in healthcare, in point of care diagnostics. And for those, you got completely different waveguide geometries and completely different demands for your product than the original low birefringent waveguide. We had, for instance, applications in microwave photonics, where our customers said, we only have TE polarization and we don't need the TM. Because in this structure, TM propagates mainly in the sidewalls of the structure and TE mainly in the horizontal planes of the structure. If you only have TE polarization, why not take off the sidewalls and generate a structure like this, which is easier to manufacture. And the easier you can keep it, the higher the reproducibility, the lower the chip cost price, higher the yield, etc. So from this geometry, different versions arose. This is a symmetric double stripe, and that's actually the one where we started in 2009, 2010, offering that in multi-project wafer runs. Currently what we're offering is an optimized version of this, and it's the asymmetric double stripe. That's actually 2 layers of nitride on top of each other, where each of them has a different thickness. And the reason why that's ideal and why we put them at different thickness, I'll show you that when we come to the slide of the spot source converters, because there's a big benefit of using 2 layers of nitride. Take-home message of our waveguide platform: low propagation loss, the ability to create spot size converters, so to play with your waveguide geometry and match that where either you need it coupled to fibers or high surface sensitivity or large evanescent field penetration. Play with that geometry and play with your mode field diameter. And very importantly, it's transparent from 4 or 5 nanometers to 2.35 microns, where some other waveguide platforms like indium phosphide and silicon, any wavelength below a micron is extremely difficult or not possible. Silicon nitride simply goes down there. And specifically for life science and sensing applications, that's a very interesting area to work in. So how do we make it? One golden rule when you started making or started developing the process for the triplex is that we wanted to make a robust, volume manufacturable process. So So you wanted to keep it as simple as possible with as little lithography steps as possible. Because at the moment you have to start aligning those to each other, that's where the yield issues will come into the picture. And LPCVD is a very reproducible process. You can grow it in batches, 25, 50 or 100 wafers at once, with a high uniformity, high quality and high reproducibility. So we start with the silicon wafer. That's for 90% or 80% of the applications, that's our core material. We also process a few silica for sensing applications that require that. But there are some design limitations to your maximum layer thickness, etc. So the preferred material is silicon to process on. Oxidize that to typically 8 or 15 micron. We put silicon nitride on it, and this version is for the asymmetric double stripe, which you see here. And this flow is to create really the square geometry as we started with. Nitride, oxide, nitride deposition, so 3-layer stack. We do lithography, dry etching of the waveguide, and in this case, basically we have the waveguide ready already. We just have to passivate it with a top cladding. In this geometry, we have to apply a second layer, locally remove that here, and then passivate it with a top cladding. But this geometry of having multiple layers on top of each other, that's also one of the design rules. Both widths are the same. So you do it by only using one lithography step only to make it as reproducible, as simple as possible. And the reason why there's a big benefit of having two stripes with different waveguide thickness is the fact that we make spot size converters. And if you want to make a spot size converter, you adiabatically change the thickness of the silicon nitride along your waveguide to have on one side a very high confinement. So we have a small mode profile, typically 1 by 1 micron. And on the other side, we got a large mode profile of typically 10 micron or 5 micron, depending on your wavelength or the wavelength and the fiber you need to couple to. In this area, that's actually where if we push down the nitride, your mode gets smaller and smaller up to a certain point when your mode starts to become leaky and it starts expanding again. That's that part of the area we're in. So the mode becomes leaky and therefore starts expanding if you make the nitride thicker. In that area, it's also very susceptible to small change in your thickness. So in the previous process which we had, in this one, we did the same tapering, but then tapered both nitride layers to a certain residual nitride thickness. The remaining nitride thickness is part of your tapering process. Here, the thickness at this side is defined by growth. And LPCVD growth is within 0.5% or 1% accurate. So you got very good control over the thickness here. Same happens on this side. Again, there it's defined by growth and therefore very accurate to control. And all of a sudden, the tapering process is somewhere in between. Yeah, and very simple, if we over taper, it simply means that this point is moving a bit. The position of the taper can change, but that has no impact on your performance. So you got a fully reproducible process all of a sudden by separating these two nitride layers and adding an oxide layer in between. In addition to the functional benefits it has on the propagation loss, it also makes the process much more reproducible. I talked about propagation losses, and I keep on showing this slide forever and ever already, and I'm actually very proud that I can still show the same slide. This is two benchmark measurements which we measured in 2011 already on two of our waveguide geometries. And this is the high confinement geometry which we standard use for microwave photonics or for high confinement in infrared, and there we typically achieve 0.1 dB per centimeter. So that's a typical loss for you can have band radii of about 50 micron. Densely packed mode profiles in the order of 1 by 1 micron. If you really start shrinking that waveguide down in contrast and make the mode loosely confined, you mimic a fiber on chip. And this is a measurement done by University of California, Santa Barbara, the group of John Bowers. And it was 0.1 dB per meter. And actually, as far as I know, the record still stands. So I haven't seen any nitride publications that went below this value. So I hope that I can still show this in 5 to 10 years from now. I doubt it, somebody will break it. But that was not our goal. Our goal is not to have this all over the wafer. Our goal is to have a reproducible, densely packed waveguide. But experiments like mimicking the fiber on chip is very helpful in pushing your technology forward. So that's the technology in a nutshell and a unique position of our nitride platform. Where the big benefit is of us as LioniX. I didn't put in a large company presentation because I didn't want to make it a sales pitch. But our unique selling point is that we vertically integrated. And that's why I started my talk with that it's not about photonic integrated circuits. It's about modules that do something. And that's what you need. You don't just need a chip. You see more and more companies popping up, facilitating the full value chain, not only supplying you with a chip, but supplying you with a module, with packaging and testing, everything around it. And this is just a flavor of some of our application we're working on, which we can mention from DNA sequencing. This, for instance, a very nice structured illumination module that defines a very well-defined interference pattern and is used for DNA sequencing by a customer of ours, Pacific Bioscience. Spectrometers for companion diagnostics, but also for OCT. We do a lot of work in microwave photonics, but today we talk about sensing. So what I'm going to talk about today is the lower three. Optofluidic sensing on a chip with a sensing element, optical coherence tomography, and also gas sensing with lasers. So if we talk about sensing on a chip, what we use is the evanescent field of the waveguide. So the evanescent field sticks out, and the three basic sensing principles, either I just measure absorption, the amount of light gets less, that's linear with the concentration of a certain absorbing material in there, so it's a very simple Lambert-Beer plot and you can measure the concentration of something. Or I can excite fluorescence. If I label first my chemicals or something that I want to measure, I first have to make that susceptible or make it show fluorescence if it's excited with a certain color. Then I can detect that fluorescent light. And the nice thing is it's always at a different wavelength with what you're excited. So you can filter it out, you can send that to a detector and measure that, and very often it's a yes or no, or even the amount of fluorescence tells something about the amount of components that you have. But even more interesting is if I don't have to treat my sample. So if I just have to have a sample of blood or saliva or anything that you want to measure, you can just put that on a chip and you have a measurement. And that, the picture here shows pretty simple. It's a refractive index measurement. However, if you use a photonic chip to do a photonic or a refractive index measurement, you basically measure everything. A photonic integrated circuit as a measurement platform is just a very dumb measurement platform that measures any change. So what you need to do then is make it smart. You need to functionalize it. So the chemistry that you put here in your sample or in the fluidics that you first have to show, let it show fluorescence, you have to put here onto your chip. Because if you look at that label-free sensing, what you have to do is make sure that, let's assume you want to detect a certain illness. The red markers here, which I want to detect in your blood or in your saliva. If I just flush the sample over the sensor, it will react to any change. So what you need to do is make sure that here the waveguides, you see them here, the nitride, the purple area, that's oxide. You need to make sure that these red markers you want to measure adhere to the silicon nitride and that you can detect any change on that top surface. And a very nice measurement vehicle for that is putting a spiral into a sensing window or putting a ring resonator into a sensing window in a small component where you can very accurately measure any changes to this sensing window. And you see two rings here, one reference layer and one selective binding layer. I'll show later in a slide what the big benefit of that is. Because in a photonic integrated circuit, you pay a certain power penalty to go on chip with anything. If you have a fiber, whether it's for telecom or for sensing, you have your light in the fiber, you need to get it on chip, it will cost you a few dB. But, it will cost you a few dB. But in the end, once you have it on chip, you're in a stable environment where you can play with reference arms, where you can play with additional building blocks pretty easily by doing system level design. So the two components which we can easily put in a sensing window is either a ring resonator or a Mach-Zehnder. You see the sensing window here in green is a ring resonator, and typically these rings have a ring response, and if I change anything to that ring, it will move. And it looks like it's a very steep curve, so I can very accurately detect the slope of that curve. I can also build an asymmetric Mach-Zehnder. So in that same footprint, and since we have a high confinement waveguide, we can bend it small around the corner. We can pack a lot of length in there and make an asymmetric Mach-Zehnder. We also have a sine-like function or a cosine-like function, and we can measure the shift in there. A gut feeling always says, look, this is much steeper and much more accurate to measure any change there. That's not completely true, and I'll show that in a later slide. But the big benefit of, or the big disadvantage of photonic integrated circuits always is that you have to get light on You have to get light on and off the chip to measure something. And that's where the tricky part comes in the picture. The chip itself is not too difficult. The platforms are mature, you can make them. The price simply scales with volume and with footprint. But in the end, you want to measure something, you have to get light on and off the chip. Big benefit of nitride is that it is transparent also at 850 nanometers. So what can you do? What you see here is actually a VCSEL. And the VCSEL comes from these guys. The mouse industry drove the price of VCSELs down dramatically, increased their volume, and nowadays an 850 nanometer single mode VCSEL can be really bought for cents. So what we do, we take that VCSEL, we integrate that flip chip on top of our waveguide, and you can see it positioned there. And here there's a detector array flip chip on that same chip. So all of a sudden I got a piece of silicon with just an electrical flex cable on it. And this becomes just a disposable sensor that after the measurement you throw it away. Or you recycle it, but you don't reuse the sample over and over. So it becomes like the glucose test for your diabetes. You put a stick in the tool, you put a droplet on it, you measure, and afterwards that's discarded. And you don't have the alignment issues anymore because your light source is an essential integral part of your sensor. And you see the VCSEL placed here. Here the light couples into the waveguide. This is just a test port. The rest goes to our ring resonators and a detector array. So this is what a sample looks like in real life. This is a sample with ring resonators and Mach Zehnders. You see here again, I said in the beginning, there are reference arms also on there. You see here this asymmetric Mach Zehnder where one of the arms does not have a coating on top and the other one does have an oxide coating. So only one of the two is in contact with the environment and with the fluidic, and the rest simply nicely fluctuates with the other one with temperature differences or any variation in pressure or anything that has an impact on the chip. So if you then look at the performance, and that's the nice thing, you saw a very steep curve of your ring resonator, and we always used to that steep curves are good. You can very accurately detect the slope. However, in signal processing afterwards, you can very accurately detect the position of an asymmetric Mach Zehnder. And there's a nice publication upcoming at Photonic West, where we discuss this also in more detail. But so these Mach Zehnders are typically about a factor of 2 more sensitive to variation in refractive index. They are a bit bigger, slightly bigger, because this ring is filling only a very small fraction, but in my definition, they're roughly the same size. So within roughly the same size, you can get a big increase of sensitivity by playing only with the geometry or with the layout of your chip. And why do you need a reference arm? Because this is a picture, a measurement we've done with on such a device with a very small concentration of ethanol in water. And the refractive index is 3.5, 10 minus 6. That's 0.005%. And at 5 points in this curve, we added a mixture and then flushed it again with water, added the mixture, flushed it again. And from the raw data, that's actually the blue one, we could not distinguish anything. When we looked at the reference ring, we saw that it was also noisy. And what happened in that is that we got some temperature fluctuations, we got some fluctuation in the laser power, etc. The nice thing is we simply subtract these two. All of a sudden, with just a very simple measurement of measuring 2 detectors and just subtracting them, you get a very clear image already of where the 5 points were, where this fluid was added. And that's again the benefit of being on a chip. In a system level environment, you can easily put in extra building blocks. You can easily put in extra sensing elements like references, like wavelength meter or wave meters or whatever, a ring to give off a trigger signal or grating or whatever. The moment you're in a stable environment, you can do these kind of tricks. So what do we have? We have a chip where you can do simultaneously multiple measurements. And you see it here coupled in with red light. This is with a fiber coupled in. There's the position for the VCSEL. Here you see 8 of these with a detector array next to each other. This chip, however, is not a sensor. It's just something that measures refractive indices. So what you need to do is functionalize it, and the biochemistry, the surface chemistry has to be developed per application. And you can, with lasers or with spotting nowadays, you can easily individual give each of these rings or each of these Mach Zehnders a different functionalization, and therefore make a chip that does 8 measurements or even 16 or 32 measurements at once. So the characterization electronics, everything available. So these kind of components, where we stand now with these kind of developments, that the photonics is not anymore the limiting factor. This is there, the chips are made in volume. We got development electronics, which is tested by our customers, used by our customers to measure the performance or develop the chemistry. But we see that in these kind of applications, you need different parts of the value chain, or the supply chain, sorry. So you need also the biochemistry to work, otherwise you will never have a product. Where a long time the photonic technology has been the limiting factor, and now you see that the biochemistry has to be developed. And once everything is developed, and you put everything in one box, that's when you can build up new applications. The nice thing now is that users can start using these kind of technologies, can start using these kind of modules for their specific design, and we lower the access barriers. I'll tell you later on that more. I'll tell you more on that later. And if you look at reproducibility then, this is already slightly older measurement of 2016. But what you see here, what we did in these kind of samples, we had 5 of these ring resonators over each other. And we functionalized them all the same, and we flushed, in this case, we had a protein in a buffer solution with different concentrations. And the nice thing what you see is that they all show the same behavior. That's also what you hope. If you individually spot them with the same material, but if you individually spot them with different materials, you will see differences. But the nice benefit is that the reproducibility of all the signals or all the different components is very high. So the technology is there. What we are looking for now, also not only here at other venues, is trying to find new applications from the application side. Find the right biochemistry partners. Showing you an example where we've done that. Together with Surfix, we're developing that. But it's finding new applications where you can use these kind of technologies. That's on one side, refractive index measurements. So there we make it smart, or we functionalize it by putting a biochemistry on the top surface. We talked briefly about fluorescence, where you make your sensor specific by putting a staining or a fluorescent label into your sample. The other way is the absorption measurement. If you have a certain material which has a specific absorption coefficient or a specific absorption spectrum, you can also measure it if you can accurately measure it. That's particularly interesting for gas sensing, for instance. And I put some spectra here from acetylene, methane, and the last one is of carbon monoxide. And what you see with typically these gases is that these are the overtones of the absorption spectrum. So the first orders are in the higher wavelengths. But the nice thing is that these materials also have overtones in the 1515 area. But what you see is that these kind of absorption spectra are extremely steep. That's defined by the molecules, it's defined by the chemistry really of the component, and they only absorb one wavelength. A very small fraction higher wavelength, and you don't see it anymore. So if you want to measure something like this, actually what you need is either a very accurate detector to measure this, or a very simple detector and a very accurate light source, where I can tune that light source to probe, as for instance scan over this peak to see where that peak is there. You can do that with bulk optic systems already. You can buy a very accurate laser, you can buy a detector, or you can buy a very accurate spectrometer, but then you get a big box, it's very cost effective, it's big, it's expensive. In the end, what you want, friends, with these kind of sensors, if you want to measure acetylene or if you want to measure methane, you want to have it in a handheld system that people who want to do the measurements or want to do the work on pipelines want to be able to measure directly. So it should be in a small system. And the trick there is actually, again, in integrated photonics. What you can do is bring together two worlds. Earlier in my talk, I mentioned indium phosphide, silicon nitride, the other technologies. If, for instance, look at indium phosphide, what indium phosphide is very good at is gaining or generating light. Silicon nitride cannot generate light, unfortunately. But what we are very good at is low loss propagation. So if we combine the two, so we take an indium phosphide gain section here, and we combine it with a silicon nitride waveguide, which light is split into two, and I got two ring resonators with a slightly different diameter. So I create a vernier of two of these resonances. You see the green one here and the blue one here. And if I tune one of these, you see already what happens here. One wavelength is fed back into that gain section. That gain section locks to that one wavelength, and you create a very simple on-chip, a very narrow line with source. By tuning one ring, you get this kind of hopping. If I tune both rings, I can also put it to any wavelength I want within that band of that gain section. indium phosphide typically, that's a C band. So I got an 80 nanometer band that I can cover by just tuning 2 of these rings. That looks like this if you package it. So here again you see silicon nitride structure. There's an indium phosphide gain chip. This one comes from HHI in Germany. And facet coupled into a butterfly package with a fiber output, such that users can use this into their manual, into their module as a laser and not as a hybrid combination. In the end, it's not interesting that there's an indium phosphide and a triplex chip in there. The user is interested in having a laser with some software interface where they can put in a wavelength or sweep it or scan it. And that's where you see it happening more and more, going into modules where you can use them for accurate sensing. For instance, combining this with a long spiral waveguide going to a photodiode. By very accurately probing. The nice thing is with these structures, you've seen it here, if you get a very large wavelength range, you can, for instance, probe 3 or 4 wavelengths quickly and have a spectral fingerprint of that gas or a mixture of gases. If you got a combination or superposition of different gases, you're looking for these individual peaks which are unique for that one gas you're detecting. So you want to be very accurately able to measure that. But we also want users to use this, and that's of course also why we're here in a, I don't say a full academic environment. I see a lot of people from industry also, but we want people to use it, to start using the technology. And that's one of the reasons why we said we need to make this also available to the public. So what we did together with Synopsys, we put this into a PDK. So what you see here at the lower right side, that's actually again these ring resonators with an out coupling here, so we can connect the gain chip here. And that's implemented now into our PDK, where you as a user can simply say, I want a laser, yes or no. If you want that, you automatically get this template, and this template fixes the laser position, because for us the assembly is easier if it's fixed, and we don't have to reinvent the package every time for you. And we started offering that of MPW201904, which actually is in production now. So again, you as a user, you don't care what's in here. You want a block that does something. I always compare it to electronic engineers who design in transistors and resistance building blocks. They build a structure with it, but they don't know exactly what the layer stack is underneath. Or some do, but in principle, you do a system level design. Same goes for photonics. We are seeing a move away from the real photonic designers into one level higher, system level designers who use software to drag and drop components into place. One last example, the last few minutes. If you think of life science and silicon nitride sensing, it's not only measuring a fluid. You can also use silicon nitride to measure signals, to process signals. And one application where we look into imaging, for instance, is OCT. Optical coherence tomography, that's where you see an uprise also of the use of silicon nitride, or at least of photonic integrated circuits, not only silicon nitride, also indium phosphide is pushing forward there quickly. And OCT is actually the optical analog of ultrasound. It's now used a lot in ophthalmology to measure your retina and your eye, where you can do the same. I didn't put the picture of the baby in here, but I always like that comparison. You have the ultrasound of babies, and from that big bottle of noise, they can really distinguish details. I was always amazed they could see I could get a daughter already in the third month of the pregnancy. And from that noise, they could really see it, and I was happy that they were right when I painted the room of my daughter in the right color. But there's not a lot of resolution. So if you want to see features which are smaller than that, with ultrasound you can't. With photonics, if you change the wavelength or if you change the frequency, you can. So you got a smaller field of view, but with higher resolution. And that's not only interesting for ophthalmology, but also for skin analysis or for other measurements. But nowadays these systems are big, bulky, and expensive. So if you look at a typical OCT system, and this is a spectral domain OCT. So in OCT, I have a light source, a sample, have it interfere and unravel it. So I do a Fourier transform. Either I can do that with a fast tunable laser and a detector, or I can have a very broadband light source that I throw in and I unravel the signal afterwards, in this case with a spectrometer. So light source, reference arm, sample arm, reference arm, interfere them again and go to a spectrum analyzer. These can be bought in bulk systems, but all three components can also be made on chip. I can take an arrayed waveguide grading to build a spectrometer. I can build a common path interferometer on chip to have very reproducible path lengths and very reproducible reference arms. So if we then look at silicon nitride, that's a nice thing. Ophthalmology or OCT is very interesting also in the 850 or 1050 nanometer range. That's where silicon nitride is very transparent. This is an example of an arrayed waveguide grading, and this is a cascaded AWG actually. So what you see here, here's the first AWG, and that one splits. In this case, we made the example of white light in a series of big bands. In each of them, there's a second AWG that separates these big bands again into a lot of small bands, and therefore I can feed all of these small bands. You see the individual outputs here, and we feed that to a CCD. Measure every individual output with CCD. We have a pixel, yes or no, and the amount of power on that, and therefore we build very accurately, very reproducible spectrometer. If you look on chip, it looks like this. So this is the realized design. The design was realized by Bright Photonics, by the way, and made in our silicon nitride platform. We directly put a CCD here of 512 channels. There's one input channel here and an output channel to go to a fiber to probe, and the rest of the output is electronics. There are more ports here, but that's just for testing and analysis. In the end, you only need one laser input and one probe channel. We built that system, we integrated that, and we're currently further integrating that. So we're working now on combining the light source also to the chip, similar to what we've done with the laser, combine the SLED directly to the chip. And at Photonic West, this is a publication which is already public of this year. We collaborate with this with the Academical Medical Center in Amsterdam. A nice overview article of the complete work which was done there. Again, a very nice publication also this year, Photonic West. So if you happen to be around, just look for their session. This one shows imaging depth of about 800 nanometers. It was designed to be 820 nanometers. Sorry, microns, 820 microns. That's fixed in the design, so it's your resolution and your number of channels. We're currently building a version that has 2 millimeters imaging depth, ideally for skin analysis, etc. And what they've measured here, this layer of Scotch tape on top of each other, and with this system they could very accurately scan over that and measure the different layers. And the module, in principle, is this size. It's a chip with a light source and a detector. So my last slide, I've shown the chip with VCSEL and a detector on it, but it's not about chips. It's about functionality. And the example I always put in there is this one. It's a mobile phone, and we all use them. Some have two, but in the end, nobody's interested in what's inside. You want to use it for their functionality. And the same holds for photonic sensors, for photonic chips. So what we should make sure of is that we make the technology available to the users to use it without having in-depth knowledge. And that's what we're currently doing, also for the sensing. What you've seen here now was the MPW at 1550. In parallel, we are working in Pix for Life, also for MPWs for visible light. And at Photonic West, we also got some more announcement on sensing MPWs. That's in a nutshell the silicon nitride platform. Any questions from your side?
Thank you very much, Arne, for your nice presentation. So the session is open for questions. Any?
Hi, thank you. So early in the presentation, you said you went to TE only for the telecom, but for the sensing applications, are you doing that with TE Lite or TM?
Both.
Both.
Depends a bit on also the source integration, what predefined polarization that one has already, and whether there's you're looking for high service functionality, high service sensitivity or large evanescent field. Our preference always is in these kind of systems to work with TE. Because your band rate can be smaller in that way. But we got the flexibility to work with both if needed.
Any other question?
And the next one is here at the front.
Hi, Arne. Thanks for your nice talk. Would you be able to provide a rough cost breakdown of this laser module integration or co-integration in your MPW? So what would be the cost of adding this laser in terms of the IMP die, the nitride die, and the assembly cost?
That is easy. In the MPW, you can answer that question easily. In volume, I can't answer it because it depends on your performance and what your volume is, etc. So there, I'm not even going to dare to discuss it with you in public about numbers because we got different hockey stick models of where we end up at high volume indium phosphide gain chips also. What we do here is we want to make it accessible to users. So what we charge, we don't charge extra for our triplex run because there nothing changes. The extra costs come in when we have to get you the gain chip and do the packaging and assembly. And there simply you pay 2,000 euros extra now to get the laser. And that's not a high volume figure, that's just to make it available for you as a customer. So you can even design the laser in it and in the end decide, I don't want to package it, I just want to test the rest and later on have it packaged. That's also no problem. Sorry?
30.
The increasing price from standard cell to standard class laser, is it 30% extra or?
Now, as said, that our cell does not get more expensive. Our cell is the same price. So if you look at this, if you talk about the MPW runs only. So in a product, I'm not even going to say to start estimating now numbers because that depends on performance and on volume, everything. In the standard cell, what we lose here is a small part of our footprint. Mm-hmm. Our triplex chip does not become more expensive. We don't charge you extra if you put a laser in. We only charge you extra for the amount of laser you want assembled. So then we put the gain chip in, we test it for you, we assemble it. And there we charge 2,000 euros extra on the packaging.
Okay, thanks.
Okay, so we need to move to the next speaker so we can, thanks again, Jörn. And the second speaker of the session is Germán Vergara. He is the Chief Technology Officer of New Infrared Technologies, and his presentation is called Uncooled